Thanks for all your efforts in digging down to the bottom of the MOF field, which is now a very large field being practiced in 100 countries or more. And so Maria's talk was so great that I'm going to skip over the introduction and take you through a slice of what these MOFs and COFs can do. But first, I want to acknowledge my fellow laureate, Michael, for that amazing talk. And I plan to skip dinner tonight so that I don't have the tor in my body. Okay. So the title of my talk is Nanoporous Materials for Carbon Dioxide and Water. And I want to address those two problems that are facing our society. This is a nice NASA satellite photo, and it shows in progressive yellow the emission of carbon dioxide into the atmosphere between January 2015 and February 2022. And as you can see, we are spewing more and more CO2 into the atmosphere. The bar you see here at the bottom is going from 392 ppm of CO2 all the way to 424 ppm. So you can see that in plain words, we are putting about 40 gigatons of CO2 into the atmosphere every year. 40, even sometimes up to 50 gigatons of CO2 into the air. And this is part of a much larger amount that is in the atmosphere as a result of burning fossil fuels. In total, we have around 1,100 gigatons of CO2 in the atmosphere right now that we need to take out above and beyond the normal amount. This is what we put into the air, and this is what we need to take out. And today I'm going to show you that there is hope, and potentially, if we decide to take CO2 out of the air, the material exists where we could do that. Water is another problem that is facing our planet. By the year 2040, the UN projects that almost 5 billion people on our planet will be experiencing water stress. That means that for more than 3 months out of the year, people will have less water than they need to sustain their life. But also, almost 1/4 of humanity by 2040 will be facing a water crisis. Crisis meaning that you just don't have enough water for sustaining life. And so we have an ongoing water problem in the world. And you can see here even places like Belgium, London, Midwest of the US is projected to have water stress because we're using more of the underground water than is being replenished. Needless to say that Mediterranean regions such as here in Italy or south of Italy and where I was born in Jordan, they're all in need of more water. So these are two problems that are facing humanity, and that's the end of the bad news. And from this point on, I will be communicating with you on the good news. And I like chemists. I'm a chemist. I think chemists are the best scientists who navigate the periodic table very well. And we showed very nicely how we can make molecules as pharmaceuticals and make lives on our planet much better and lengthen the span of life, okay? That's just one example of how powerful it is to take atoms, link them together to make molecules that end up saving lives. And what I want to say here is that in my research, when I started back in the early 1990s, we asked the question, what happens if we take molecules and start stitching them together like Legos, but with strong bonds? Everybody was looking at molecules with weak bonds because of their importance in biology. But what about if you take those molecules and you start stitching them together with strong bonds? What could we make? And what could these be useful for? Well, that gave rise, as Maria beautifully illustrated in her presentation, gave rise to what we call reticular chemistry, which is the chemistry of linking molecular building blocks by strong bonds to make crystalline structures. There are three very important components in this definition. One is that we're building molecular building blocks like Legos because we want to put some rational thinking into how to make things by design. The second thing is strong bond. If you're going to make materials that are going to take CO2 out of the air or water out of the air to make drinking water, you want them to be there for years functioning over and over again in a cyclable manner so that they don't create their own environmental waste problem. And so the strong bonds, again, from chemistry, translate into longevity of the material and the material's ability to cycle over and over and over again for many years. And crystallinity is the blessing of humanity because it allows us to figure out where the atoms are in our creations and learn from that. So crystallinity is a very important component, and in some cases like water harvesting, it is a requirement for our ability to carry out water capture from the atmosphere with energy efficiency. The result of reticular chemistry has been MOFs, already introduced by Maria. The yellow ball indicates the space within which you could incorporate the material. The blue regions are the metal oxide units, and the organic is linking those metal oxide units together. It's exactly like Lego in making different forms. And back in 1995, we showed that they can be crystallized. And in 2005, we showed that, in fact, you could make these entirely from organics. And our ability to design materials or to precisely put together these building blocks have also led to many other classes of materials, some of them such as molecular weaving. I won't talk about that today, but this is another amazing story that deals with materials and how to make materials harder but also tougher, less brittle. That has its own world of application. Today I will show you the one application for MOF and one application for COF. But strong bonds and the building block approach are the key contributions here for the development of this new chemistry. Well, these materials look like baby powder, or you can say granulated sugar. And if you zoom in, as this movie illustrates, done by BASF, zoom in on the atomic level, you find that the framework is riddled with holes. The crystal is riddled with billions of holes. And the structure is a scaffolding. And the idea is that could we design them like magnets to pluck out water out of the air to make drinking water, or pluck out CO2 out of the air to make to clean the air. And this is what we've done. And this is what I'll show you. Okay, this is supposed to be a movie rotating, but it's not going to rotate. If it does rotate, then you'll see that, in fact, the interior of the framework is quite open. It's a scaffolding. It's a scaffolding, and so things can move in and out with great facility. We measured how fast water can move inside one crystal, and it turns out to go in and out in a nanosecond because it's a very open structure and the pores never get clogged. And the reason they have extremely high surface area, as Maria has very nicely illustrated with the football field, is because everything you're looking at in a MOF structure or a COF structure is a binding site onto which gases can bind. And if I can create a material that's like a magnet that can bring gases together, then I can concentrate those gases onto the internal surface of the material. Gases like to repel each other, and that's why they fill large volume. But if I introduce a material that loves, let's say, CO2, then I could concentrate CO2 inside its pores. Just like, let's say, bees on a honeycomb. Okay, if you create an attractive surface, then gases will be packed onto that surface. So this is what they look like. After the first report of MOF and the breakthrough that we made in terms of their surface area, BASF actually thought that that paper in '99 was reporting a surface area that was a misprint because it was 2,900 meters square per gram. We had broken 1,000-year record of porosity that was held by carbon. And we were 6 times more than the porosity of carbon, and they thought it was a misprint, and that started a collaboration with BASF. They told me that they were reproducing our compound, and that in fact they were getting even higher porosity than what I was reporting. And in those days, we didn't really, weren't very good at evacuating the pores from the stuffing that goes in, the solvent molecules that go in during the making of the material. So, so by now, that MOF5 has actually a surface area of 4,000 meters square per gram, okay? So this started a collaboration with BASF that showed that these materials are not, as people in those days used to say, boutique materials. They are not boutique materials. They are materials that you can make in ton quantities. And that was a very important demonstration that these could then be taken into applications. So I want to talk about carbon capture. What does it take to make a viable carbon capture material? One is that you need high capacity. Well, that's easy for a MOF because you have a very high surface area. So it's going to take up a lot of gases. High selectivity. Well, reticular chemistry's hallmark is that you can go into the pores and design and basically manipulate them almost on the atomic level. You can surgically insert groups onto the surface that can dictate what kind of molecule to pluck out that CO2 molecule out of the air. The idea of taking CO2 out of the air in popular terms could be stated in the following way. You have one CO2 molecule for each 2,500 other gas molecules in the air, nitrogen, oxygen, others, and water. And that's the difficulty that we're trying to overcome. So we need a highly selective material. I'll show you how we can do that. We need the material to be water stable because wherever there is CO2 in combustion gases, there is water. There's water in the atmosphere. We need it to be oxidatively stable, stable to oxygen. It needs to be cyclable over and over again, durable. And it needs to have low regeneration temperature. If you have to heat the MOF to 100 degrees or 200 degrees to remove the bound CO2 or the bound water, then you're putting in too much energy. It's costing you, it's not economical anymore. It's costing you a lot of energy and it's not economical. And it needs to be scalable. If it's not, as my computer science colleagues always tell me, if it's not scalable, it's not worth doing. Okay, and so I've come a long way since the beginning. And now none of what we do is not scalable. We aim to make it scalable, so that's very important. So this is the experiment that we try. Very simple experiment. Take air that contains extra carbon dioxide, pass it through the material, and then look at the composition of what comes out on the other side. If you find CO2 on the other side, then your material is lousy on capturing CO2. If you don't find CO2 on the other side, then you have a chance of having a great material. Okay, so I'm going to skip many, many years. We've been working on carbon capture since the mid-1990s. I'm going to skip all of that work, but only to tell you that that work was valuable. All that basic research was valuable on understanding what would CO2 do inside the pores of a material, the chemistry of CO2 in the pore. And so we settled on this important compound. We discovered back in 2019 that we can crystallize COFs from some of the strongest bonds in chemistry, double bonds, carbon-carbon, double bonds, carbon-carbon bonds, and carbon-nitrogen double bonds. It turns out that this material is so durable that even if you put it in concentrated acid like HCl or concentrated base or corrosive media like N-butylithium, it's unchanged. So it is extremely stable, and that's the sort of stability that you need in order to address a major problem like the capture of CO2 from air. Okay, so based on this material, we modified the pores. I won't go through all this nitty-gritty chemistry. We modified the pores to put polyamines covalently. We attached them covalently or strongly into the backbone of the material. We need these amines because they're the selective elements that bring the CO2 in. Without those amines, you're not going to be able to pluck out CO2 out of the air, okay? So we made this material. Recently, we reported it in Nature. And how does it do? Okay, so the student did all the tests in the lab. They look really good. And I looked at him and I said, your data is so great. Why not pipe in Berkeley air into the material and prove to the world that, in fact, your material is pretty good? And he said, well, it's a wonderful idea, Professor. So the next day, he had, what he has done, he piped in, this is the student fingers. I always tell students that the hand is very important. It's like when you watch on TV the people who are selling products, jewelry, the hands are featured prominently. And so he listened to me and he demonstrated here, modeled, this is what the compound looked like. This is Zihue. It's a very nice free-flowing powder, yellow powder. But okay, so this is the air that came in from Berkeley. CO2, you can see it varies between 450 ppm to even sometimes 500 ppm. He said that it was raining one of those days, and when it rains, the sun is not out, and so the trees are not taking up CO2, so the amount of CO2 in the air is higher. And then he measured also the humidity during this 20-day period. During this 20 days, he did 100 cycles. Okay, and what he found is that as the humidity goes higher, so does CO2, okay? When the humidity is lower, so does your CO2 uptake. But nevertheless, you're taking up CO2 on all humidity levels. And the material, when you compare it, as I'll show you shortly, at the same humidity, it does not degrade as you cycle. That was a huge discovery, okay? Because many materials, after many cycles, they degrade. And when they degrade, you can't carry out 100,000 cycles or 200,000 cycles, which is what you need as a minimum requirements for commercialization of these materials. Why does it scale with the humidity? Because what we discovered is that with the humidity, CO2 binds to those amines and it makes carbamic acid and makes bicarbonate, which is great because that's a ratio of 1 CO2 per single amine. When it's dry, you make carbamate. Well, carbamate requires also a cation, and it uses another amine for it. So you use 2 amines for each CO2. So in fact, water helps in shifting the equilibrium towards that 1-to-1 ratio between amine and CO2. And you can, as much as we can do, under a humidity level of 37, you can see that the performance of the material is maintained from this cycle all the way to 94th cycle. This is the capacity of the material, 2 millimoles of CO2 per gram. The minimum for commercialization is 1 millimole of CO2 per gram. So we're doing double what is required. But not only can you do it from air, but you can also do it from point sources. From a power plant that burns natural gas, this is what our capacity is for COF 999. For coal flue, it's also about 2 millimole of CO2 per gram. So here we have a material that cycles more than any other material reported in the literature. And I imagine that this will cycle hundreds of thousands of cycles without degrading, because the backbone is made from durable framework and with, as I mentioned, the strongest bonds in chemistry. So what does this look like at scale? Okay. As I mentioned, we have about 1,100 gigatons of extra CO2 in the air that we need to capture. This is the properties of our COF. It takes 2 millimoles of CO2 per gram, and it cycles around 10 minutes per cycle, meaning CO2 going in, CO2 coming out. By the way, after you store the CO2 in the MOF, the idea is that you can compress it, take it out, compress it, and then pump it under the ground. That's the only way we can do it today for carbon capture. Until we found a way of taking CO2 and convert it to something useful. We will continue to pump it under the ground. So this is what I want to say, is that if you make 100,000 tons of cough and you make a carbon capture plant out of that, you'll capture 0.5 gigaton of CO2 per year. Okay, now, if I put such a plant in each city of 1 million or more, I can capture all the extra CO2 in the air in 3.5 years. And before you say, well, Omar, that's a lot of material. It is, but so does our chemical industry, is able to work at that scale. And if you don't want it in every city of 1 million or more, you can put it in 2 million or more population. That's around 200 cities in China, US, and Europe. Only those 3 places. That's 11 years. Okay? It's doable, isn't it? We produce sulfuric acid around the world. Our annual production of sulfuric acid is 200 million tons. Surely we can do this, okay? I'm not saying it's simple. Society has to believe in it. For us, believe that it's a crisis before we can solve the problem in this kind of time scale. But the material exists to do this. And it's a result of the cough chemistry. Now let's imagine that Zihui doubles the uptake of the material. He figures out a way of doubling the uptake, which I think he might have done, because we understood that water goes into the pores along with CO2, and it aggregates, and was blocking the pores slightly, and that's why he's not utilizing all the amines or the potential of the material. So now, as he opens the pores larger, he's within reach of doubling the uptake. When you double the uptake of the cough, all these numbers fall in half. Now it's even more doable than before. So what I'm trying to say here is that this is real. Okay, this is real material that's tested in Berkeley open air, and it demonstrates in terms of durability and cyclability like no other material. So we need to scale it up, and we already are piloting materials for carbon capture in many countries in Europe and the US. And so as soon as this is scaled, then it could be placed in those pilots right away, okay, where right now there are slightly inferior materials. Okay, so the next problem that I want to address is the water harvesting problem. There's a lot of water in the air. There's about 13,000 cubic kilometers of water in the air at any one time. There's more water than we have in rivers on our planet. And before you tell me that this is going to dry up the air, it's not. We're taking water out of the water cycle, natural cycle, and putting it back in. It doesn't get destroyed at all. The same water goes back into the cycle. And if we were to give each person on our planet 50 liters of water a day, we would have only used less than 0.01% of the water that is in the air. So we've got plenty of water in the air. But could we use that water as a new source? Could we use the air as a new source of water? Okay, not every day do you have that possibility. But this is now becoming real. Okay, so again, cutting out a lot of basic science that we've done is that we made a material from aluminum organic, okay? This is the material made from aluminum oxide rods linked by perazolate, very common linker, not exotic. The material takes up water at 5% relative humidity, and a lot of water at around 10% relative humidity, okay? That's like an inhumane humidity. I mean, it only exists in the most remote areas of the world. Most deserts or most arid regions of the world have humidities in the summer of 20% relative humidity or more, okay? So this is even better at taking water out of the air. Now, We do, of course, X-ray crystallography on these to make sure we know what the structure is on the atomic level. And so what I want to say is that I'm going to show you where each water molecule that enters the pore resides. That was a very important study because it made us understand the mechanism by which water enters the pore and its behavior within the pores. You need to do that if you want to design the best materials for a particular application. And so if you are a water molecule floating in the pore and looking around, what you'll see is a grid. You'll be wrapped in a grid of hydrophilic and hydrophobic regions that alternate: hydrophilic, hydrophobic, hydrophilic, hydrophobic. And in one granule, you have billions of these grid regions in a grid. So what happens, and I'll show you the movie where these water molecules go, is that the first water molecules clearly go to the most hydrophilic regions. They fill the hydrophilic regions, and you'll see that after they fill the hydrophilic regions, they bridge over the hydrophobic region. Of course, the hydrophilic regions are water-loving. The hydrophobic regions are water-hating, right? They repel water. This pull and push allows you to control the temperature at which water could be removed. And it's the key of why you can remove the water from the moths just by ambient sunlight in the desert, so 45 degrees Celsius, okay? So this is what it looks like. It's a grid, and now I'm going to excise out one pore and then slice it so that you can see what a molecule would see. And you'll see the first water molecule going hydrophilic site, second hydrophilic site, third hydrophilic site, and then a fourth, and then now it's bridging over the hydrophobic site through hydrogen bonds. And then the pores get filled and concentrated with water. And the mechanism is cooperative. The very first water molecule helps in bringing in the second one, the third one, the fourth one, and the rest of the water molecule into the pores. In fact, if you looked at the isotherm of the water uptake, you'll recognize that it's not too dissimilar from oxygen going into hemoglobin. It's a cooperative phenomena that is facilitated by the very first water molecule, which we do not take out of the moth. It's a seed onto which other water molecules bind, and it stays in the moth. We never drink that water. That stays, that single water molecule is the seed onto which the other water molecules bind. And it's the strongest bound molecule to the structure. So these are my heroes. These are the ones that are at the frontier. These are the ones making discoveries. And they got me to agree that they should go into the desert to test the material. Okay, take it out of the lab. So they designed, so they went to one of the driest deserts in North America, the Death Valley, and they made a device from pancakes of moth. And this is during the night, it's exposed to the air, and the moth extracts the water from the air. The pores get filled with water, as I just showed you. And during the day, they'll close it, they close it, and then it heats up under the sun. And they can extract water from that dry air, okay? We're generating water with no energy input aside from ambient sunlight, okay? And this student, Eugene, decided to drink the water. I didn't encourage it.
All right, ready, 2, 3, action.
Cheers. Nice.
Okay, it's distilled water, so it's not as nice. To Eugene, it's honey, because it's his result. It's a beautiful result. This water was harvested from Arizona desert, and we tested it for organics, metals, anything that may have leached from the moth, and absolutely nothing. This is an ultra pure water. This is the cleanest water you'll ever make. Really, because it's the moth the pores of the muff only allow water in. If you have this next to a gas station, there are octane molecules floating around, it won't go in the pore. Okay, so this is molecularly designed for water. So, okay, that's how you can harvest water with no energy input aside from ambient sunlight, but some of us are very impatient like me. I want more water and I want it now. So you can just electrify it. You design a system that's electrified. This machine is no larger than a microwave oven. It works in the same way I described before, except it's automated. It has 200 grams of moth, and you can see the harvested moth is going to be collected at the bottom. Basically, once the moth is filled with water, you heat it up, and then it can be condensed. And you can make 5 liters of water per day, okay, from 200 grams. Every day. And this has been running for 3.5 years. Okay, every day, and the material is graded for about 6 to 7 years. Okay, so everything about this machine is off shelf. Okay, it looks complicated because this is one of our older prototypes. The more current ones are much simpler. Here's another machine that we're testing now in certain parts of Texas and California. It gives us 22 liters per day, and it employs 2 kilograms of moth. Okay, every day for 6 to 7 years. So this moth has been cycling over 350,000 cycles. Okay. Now chemistry comes in and says, well, okay, if I could have these machines deliver 50% more water or more water, then more people can have water, right? And this is not just for people who live in the desert like I used to when I was a child. But this is for everybody, because if it works in the desert, it works also in the humidified regions of the world where water may be plenty, but it's not clean. Our drinking water in California has PFAS. Yours probably has also PFAS, okay? So you can have your own device, and you can have control over your own device. So as a chemist, we're always interested in more, okay? More water into the pores. And we love MOF 303. Nikita loves MOF 303. He worked on it for 4 or 5 years, okay? And we love everything about the binding sites, about the energetics of the system. And so we wanted to make it larger, but not too large, because if the pores get larger into what's called a mesoporous regime, then you get a 2-step isotherm, and it's not very energy efficient to take the CO2 out of the water. Out of the water out of the MOF, excuse me. Too many things keep straight in my mind. So we inserted 2 carbon atoms, and that gave us 50% more water. Okay, it gave exactly the same structure, but like Michael's Tor, it's just more larger. Okay, just like it was larger cells, it has a larger. Okay, so that's our Tor, 2 carbon atoms in the linker. So how does this look like at scale? Okay, for the independent water harvester, as my student called it, the one that only works on ambient sunlight, 1 ton of MOF with no energy input gives you 3,000 liters of water per day, every day, for 6 to 7 years, at 1 cent per liter. Okay? An active water, the one that is that's electrified, for that 1 ton, you can deliver 60,000 liters of water per day, every day for 6 to 7 years at less than 2 cents per liter, depending on the cost of electricity where you live. Okay, so that's what we're looking at. That is what we will be realizing within 6 to 10 months in terms of large production of these harvesters. Okay, so I've spent all my life, all my adult life, working on this. Okay, that's, if you just count from the early 1990s, that's around 35 years. Okay, there is no need for us to wait 35 years to make discoveries that change our lives. And so I've met a colleague in computer science, Jennifer Shays, And I was explaining to her about my work, and she said, "Do you use AI?" And I said, "I know nothing about it. And I don't think it's very helpful because it's not ready for chemistry. It's not ready for prime time in chemistry." And she said, "Without AI, your discoveries will never reach society because you have to scale, okay? And you can't scale if it takes you 35 years to discover something." So I'm completely sold. I have now converted almost 75% of my group to do AI-related chemistry. Okay, so if they can't blend AI into their chemistry, they cannot join my group. That's basically what I decided. And it's been an incredible, incredible change because we also raised money for a new institute with Jennifer that develops the whole idea of AI for science, but specifically to accelerate breakthroughs in water harvesting and CO2 to address climate change. I'll show you 2 slides and I'll finish of the results. We are building what I call the AI discovery cycle. The AI discovery cycle is nothing more than robotics. In this case, we're looking for new crystals, and we image recognize these in an automated fashion to look for crystals. We build our data sets, and then we make the normal machine learning algorithms more chemistry intelligent. So we put into them different parameters that chemists think about. And then we look at, well, what does the machine learning algorithm give you in terms of conditions under which to discover new materials, okay? And the results have been breathtaking. Already, we can do 50% better than what we've been doing before, okay? In the language of computer scientists, better than random, 50% better than random. I mean, look, research into new materials is rather random, isn't it? Okay, but we're doing a lot better than that already. So the second thing that we've been doing is that same student that went to the desert, Zach, has also been developing LLMs in my group. He developed 7 LLMs, 7 ChatGPT routines, just through conversational language, and built an entire research group, okay? A group that will do about everything that our research group does, whether it's reading the literature, giving instructions on what to put together, we'll analyze the result, make the stuff, even 3D print the glassware or the labware, and reprogram the robot using ChatGPT. So 7 ChatGPT come together to solve a problem that we wanted to solve, which is a cough. We have conceived a cough shown here that would be great for water harvesting. It would take a student in my lab, supposedly an expert lab in mouth and cough, okay? It would take them 2 to 3 years to crystallize that cough. It would take a group that's not familiar with mouth and cough much longer. And just using these 7 LLMs, they went from experiment 9, where they have no crystallinity, to experiment 84, where they made crystalline structure. That took 2 weeks. So this is completely revolutionizing the way we do chemistry, at least in my lab. And I'm trying to compel my colleagues to enter with me through this blending AI into the laboratory tasks, but also the very thing that we care about, and that is to accelerate discovery. I just showed you those 2 examples. Well, these are my heroes, as I mentioned before, and I love working with students, and I think they like working with me. I'm not a very easy professor, but they seem to appreciate the rigor and hard work, and the financial support. And I want to thank you, and it's an honor to receive the prize. And again, Maria, thank you for that incredible introduction of our work. Thank you all very much.